Dear students, very good morning to all of you. In continuation with the characteristics of an operation amplifier, in this session we are going to discuss about the applications of the operation amplifier. OpAmp applications can be categorized into two types. One is linear applications of the operation amplifier. Another is non-linear applications of the operation amplifier. The applications which comes under the linear applications are, one is how OpAmp can be used as an inverting amplifier, how OpAmp can be used as a non-inverting amplifier, how OpAmp can be used as a voltage follower, how it is used as an summer, how it is used as differentiator, how it is used as an integrator, how it is used as a comparator. These are all linear applications of the operation amplifier. Non-linear applications of the operation amplifier are precision rectifier, how OpAmp can be used as a logarithmic amplifier, how OpAmp can be used in the building of a Schmitt trigger. So these are non-linear applications of the operation amplifier. As per the syllabus prescribed by VTU, you are going to study only the linear applications of the operation amplifier. So let's start with the inverting amplifier. How OpAmp can be used as an inverting amplifier. Dear students, first of all try to understand how to build up the circuit for the inverting amplifier. So look here, as you know, OpAmp is an basically differential amplifier which can amplify the difference of the two input signal. You know the symbolic representation of the operation amplifier. Write the symbol of the OpAmp which has two inputs, single-ended outputs, and two supplies plus VCC and minus VE. That is a symbolic representation of the operation amplifier. As in the application of an inverting amplifier, input signal is applied to the inverting terminal of the OpAmp. In the figure you are observing, input signal Vin is applied to the inverting terminal of the OpAmp through the input resistance R1. There is a feedback element RF which is connected between output and input. So this feedback element which links the output with the input. And the type of the feedback used here is negative feedback. Dear students, negative feedback always used in the amplifier. Positive feedback can be used in the oscillator circuits. And in the circuit you are also observing that the two terminals, inverting terminal is referred as an indicated by A, non-inverting terminal is indicated by B. And non-inverting terminal is grounded or earthened. Okay, and virtual ground concept. According to virtual ground concept, whatever the voltage which present at the terminal B, same thing will be carried out at the terminal E also, which means voltage at the terminal B is 0 because terminal B is grounded, non-inverting terminal is grounded. Since VB is equal to 0, VA is also equal to VB is equal to 0, and no current, no base current flows. Okay, then we are going to derive the expression for the output voltage. In order to derive the expression for the output voltage, we have to apply KCL, Kirchhoff current law. Sum of outgoing current is equivalent to sum of incoming currents. So here, sum of the incoming currents to the node A is I1, and the current which is going, outgoing current from the node A is IF. Understood? And also IB. Since IB is equal to 0, we will get I1 is equal to IF. Understood? Now, apply KVL to input loop and output loop and find the value of the current I1 and IF. To find the value of the current I1, we need to apply KVL to the loop containing the nodes Vin and A. If you apply KVL to this loop, you will get Vin minus I1 into R1 minus VA is equal to 0, implies that I1 is equal to Vin minus VA divided by R1. As per virtual ground concept, VA is equal to 0, therefore I1 becomes Vin by R1. Similarly, find IF by applying KVL to the feedback loop. You will get VA minus IF into RF minus V0 is equal to 0, implies that IF is equal to VA minus V0 divided by RF. Again, as per the virtual ground concept, VA is equal to VB is equal to 0. Substitute the VA value in the expression of the feedback current. You will get IF is equal to minus V0 by RF. Now equate these two currents as per the KCL. You will get V in by R1 is equal to minus V0 divided by Rf. So from this equation we can evaluate the term V0. So V0 becomes minus Rf divided by R1 into Vn by applying the cross multiplication. So this is the expression for the output voltage of an inverting amplifier. And the voltage gain of this inverting amplifier AV is equal to minus Rf by R1. Negative sign indicates that output is inverted. So in the waveforms you are observing that the first one is the input signal. So input signal of some 2 volts peak to peak and 1 kilohertz frequency assume, and output will be same but it is inverted. Output is inverted with respect to the input, which means the phase shift between output signal and input signal is 180 degrees, but the amplitude remains same, indicates that voltage gain is equal to 1. So if the voltage gain is equal to 10, then the amplitude of the output is 10 times more than that of the input signal. Okay, this is about the inverting amplifier. And next we will see non-inverting amplifier. Non-inverting amplifier. So non-inverting amplifier is, it is completely opposite to that of the inverting amplifier, which means output of this non-inverting amplifier remains the same as that of the input signal. There is no phase shift between the output signal and input signal, okay, because it is a non-inverting amplifier. So in the non-inverting amplifier we are applying the input signal to the non-inverting terminal of the OpAmp. Dear students, we call the non-inverting terminal is B. To the terminal, to the point B, we are applying the input signal directly, and as per the virtual ground concepts, VB is equal to Vin, which is also equal to VA. So that VA is equal to VB is equal to Vin. Now use the same procedure of inverting amplifier. Find out what is the Kirchhoff current law. How to apply Kirchhoff current law to this non-inverting amplifier. But by applying KCL to this non-inverting amplifier, you will get IF is equal to IB plus I1. Since IB is equal to 0, IF is equal to I1. Call it as equation number 1. Now find out what is IF, what is I1. IF is the feedback current. See the direction of the current. Based on that, you should apply the KVL. If you apply KVL, you will get, if you apply KVL to the output loop, you will get V0 minus VA divided by RF is equal to IF. Is it right? So as per the virtual ground concept, VA is equal to VB is equal to Vn. Substitute Vn in place of VA. Okay, you will get IF is equal to V0 minus Vn by RF. Then what about I1? To find the current I1, apply KVL to the loop containing the nodes A and ground. We will get VA minus 0 divided by R1 is the current I1. Now equate these two values of the current in the equation 1. You will get Vin by R1 is equal to Vn by R1 is equal to V0 minus Vn by Rf. So now separate the V in terms. You will get 1 by R1 plus 1 by Rf into Vn. That is equivalent to V0 by Rf. Okay. Now take the LCM on the RHS side. You will get R1 Rf as a LCM. Then Rf plus R1 by R1 Rf you are getting on the RHS. Then Rf cancelled on both sides. You will get V0 is equal to Vn into Rf plus R1 by R1. Divide Rf and R1 by R1. You will get 1 plus Rf by R1 into Vn. That is your output voltage. So the expression for the output voltage in case of non-inverting amplifier is V0 is equal to Vin into 1 plus Rf by R1, and divide both sides of the equation by Vin. You will get the voltage gain AV is equal to V0 by Vin is equal to 1 plus Rf by R1. In this case, your voltage gain is positive, which means that the output is not inverted with respect to the input, and the phase shift between the output signal and input signal will remain 0. Next application is that how OpAmp can be used as an voltage follower. Dear students, so in the voltage follower circuits, as the name tells you, output voltage follows the input voltage, hence the name voltage follower. In this case, there is no feedback element or input resistance we are using here. Input signal is directly connected to non-inverting terminal. and feedback is connected between output and the input terminal V1, that is inverting terminal of the OpAmp. As per the virtual ground concept, if you apply the virtual ground concept, V2 is equal to Vin is equal to V1. Since V1 is equal to Vin, output voltage, there is no feedback element between the output and input, therefore V0 is equal to V1. Since V0 is equal to V1 means V0 is equal to Vin, because V1 is equal to Vin as per virtual ground concept. Since then output voltage is equal to input voltage, the output voltage follows the input voltage. Divide both sides of the equation by Vin, you will get V0 by Vin is equal to 1. Indicates that voltage gain of the voltage follower is always equal to unity. Keep this point in your mind. So voltage gain of the voltage follower is always equal to unity. There is no phase shift change, there is no magnitude change. The amplitude and the phase shift of the input signal and output signal remain same. There is no change, indicating that voltage gain is always equal to unity. Okay, so these are the first three applications of the operation amplifier. So these applications are very important for examination point of view. Either they ask you to explain these applications, or they may ask you to solve the problem on the inverting amplifier or non-inverting amplifier. Okay, next we are going to see a few more applications of the operation amplifier in the next class. Thank you.